Okay, so this is part 4 of deriving C5h character table. Kind of a crazy one. We are moving right along. So far, where we got in the first 3 parts is we're able to derive these 4 irreducible representations. And we figured out lastly that x1 x squared minus y squared um, transformed as this irreducible representation that they transform together. And so what we have to do next is start thinking about other quadratic functions, and multiplying things by z is going to help us. Z is a one-dimensional irreducible rep, and so if we multiply one-dimensional irreducible rep by a two-dimensional irreducible rep in order to try to generate another irreducible rep, we'll get back a two-dimensional rep. And so we're going to look at xz. Right, that's another one of these d-orbital functions or quadratics. Well, we know x and y transform together, so if we multiply it by z, that's going to tell us yz is going to transform together with xz. And so this ends up being quite straightforward because you could think about, okay, we did all the math 2 videos ago to see how x and y transformed. But z didn't do anything. So if we're multiplying by z for identity, of course we're going to have a 2 here, but z didn't do anything when we do a C5 on it. And so we're going to get the same character as what we had for xy. So this is going to be copied through when we have positive ones for xy. So we just copy these ones for our third gamma, gamma 3 here, that had xy. And same thing with C5h and C5h. Just copying them through 2 cosine 4 pi over 5, 2 cosine 2 pi over 5. Now, things are going to change when we get to sigma h. Sigma h, we have a negative one there, right? So that means z went to negative z. If you recall, x went to x and y went to y. This is for sigma h. Remember, sigma h is in the xy plane. It's perpendicular to our principal rotation axis, our C5. So it's in the mirror plane here if this is x, y, z. And so if we have a vector z, flips it down to negative z, and x and y stay the same because they're in the plane. And so what that means is that xz went to negative xz, right? Because z went to negative z, and yz went to negative yz with sigma h. And so our character here is going to actually be -1, 0, 0, right? Our 2 by 2 matrix. That's what explains going xz takes x, y, z and goes to equal sign there, negative x and negative y, z. So take the trace across the matrix, and you get that chi, the character of sigma h, equals -1 plus -1, which equals 2, equals -2. Sorry. So I put a -2 here. And another way we could have figured that out was just say, well, look, x and y transform a certain way. They transformed as a 2 up here, right, x and y, and the transformed as a negative that, the negative z component. So you could get this by just going 2 times -1. So we're going to use that trick for the rest of these here. All these are just going to be negatives of the values that we got for the gamma 3, the xy. So this is going to be -2. And it's because there's a sigma h embodied in these all these s's in these improper rotation axes that takes z to -z. So this makes sense. So -2 cosine over of 2 pi, -2 cosine 2 pi over 5, -2 cosine, oh, I'm just taking the negative of that one up there, 4 pi over 5, and -2 cosine 4 pi over 5, and -2 cosine 2 pi. Okay, and so at this point, we very quickly derive this reducible representation. There's one more that we have to derive, as it turns out, and we keep testing functions, and we actually have most of the quadratics here figured out. we have xy, x squared minus y squared, xz, yz. There's one more d orbital, right? And that's the z squared. But that's not going to help us anymore. And so it was not going to generate something new. And so the one that actually helps us generate something new is a cubic function. And it's looking kind of crazy, but it's x, y, z. And so what we're going to do is we're going to think about that as just z times xy, which we derived earlier, right? And so we can do the same sort of trick where we're just going to get 2. It's telling us it's going to be a dimensionality of 2. And what is it going to be? It's going to be x, y, z is going to transform as z times this. So x, y, z is going to transform with z x squared minus y z y squared. It's a cubic function. Okay, these are f orbital functions. Just z times this. But those are the two functions that are going to transform together, but we don't really have to do much math. We just take z and times it by gamma 4, what we're calling gamma 4 now, which is this one here that transforms x, y, x squared minus y squared. So here we have 1s across the board, the first 4 on z, and for x, z, and y, z, we have these values here. So we're just going to copy these values here because we're just multiplying by z, which is all equal to 1. So it ends up being these values here. It ends up being pretty easy. So we just take 2 cosine 4 pi over 5. And again, you see this alternating with the 4 pi over 5s and 2 pi over 5s. Some patterns here. We're just copying these over from this line here. And we do the same sort of trick. We have a positive 2 here and a negative 1 here. And then we have a bunch of negative 1s for z. So we're going to be the negative of this line here. Negative 2. Negative 2 cosine 4 pi over 5. Negative 2 cosine. See a mistake here. This is it a mistake? No, it's not a mistake. Good. 2 pi over 5. Negative 2 cosine. I'm just copying from here. 2 cosine 2 pi over 5. And putting negative signs in front because of the negative 1 and the z. Negative 2 cosine 4 pi over 5. And you can see this has some negatives, but it's different than this one above. And so at this point, you can test other functions, but you're done. And what you'll notice here is the total number of dimensionalities here is actually 10. That's how you know you're done. 2 plus 2 plus 2 plus 2 plus 1 plus 1 is 10. That equals the number of classes. But there's a few problems here. One problem is we're violating actually 2 character table rules. Okay. One of these rules that we're violating is that the number of classes doesn't equal the number of rows, the number of irreducible representations. We only have 1, 2, 3, 4, 5, 6 rows. Okay. And we have 10 classes, 10 columns. So that's violated. We also don't have the sum of the squares of the dimensionalities equaling the order of the point group, which is 10, right? So that's one of our character table rules. Another one of the character table rules, these mathematical relationships that always have to be true for character tables. If you don't know where that's coming from or you're interested in learning more about the character table rules, you can check out the other video, character table rules that I have. But basically 2 squared plus 2 squared plus 2 squared plus 2 squared plus 1 squared plus 1 squared doesn't equal 1 plus 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 1 10 times, right? And so the way we got to fix this, and that we're going to fix this, is by breaking up each of these elements, these vectors, into imaginary components. So we're going to do that. But before we do that, we can actually at this point assign Mulliken symbols instead of these gammas. It's enough. We have enough information to do so. And you want to assign these at this point before you break them up, break up these dimensionality 2 ones. So we call these A or B. We're going to call both these A. We call them A or B if the dimensionality of the character under the identity is equal to 1. These are Mulliken symbol rules now. I have a video on that. And we use an A if we're symmetric, if we're positive with respect, positive 1, with respect to the principal rotation axis, which we are on both of these. We would give it a B if we had a negative 1. And then we're going to use a prime notation because we have sigma h in this point group. So if we're perpendicular with, if we're symmetrical, positive 1, with respect to the sigma h, we give it a prime. And we give it a double prime, negative 1, if we're antisymmetric. And then we have dimensionalities of 2. And for dimensionalities of 2, we give it an E. And so we give it a value, again, of prime or double prime. And so here we're symmetric. So we're going to call these prime. And here we're antisymmetric, negative values for sigma h. So we give it double prime. Now we still can't have things called E prime, two things called E prime or two things called E double prime. That's confusing. So we call one of these a 1, and one of these a 2, and one of these a 1, and one of these a 2. And I follow the convention that people use for character tables here, which one to call E1 prime, which one to call E2 prime, which one to call E1 double prime, which one to call E2 double prime. Mulliken symbol rules aren't really well defined here, so you just got to make sure that you're speaking the same language. But at the end of the day, it's the vectors that really matter, the values of the vectors, not what we call them. That's just arbitrary. So moving on from here, what we're going to have to do is we're going to have to take something like all these E vectors, we're going to have to actually eliminate them and break them up. So this E1 double prime, we're going to have to break up into two components containing a dimensionality of 1, two one-dimensional components. And the problem with this is that there are no real functions that transform like this. If there were, we would have found them. Right? We tried all these different linear functions, x, y, and z, tried the different quadratics, even some cubics. And there are no real functions that transform like this. So in order to satisfy the character table rules, what we're going to be working with now are imaginary functions. And we're going to get complex characters, right? Non-real characters here in some of these cases where we actually have real and imaginary parts in the character table. And so that's going to break these up. So these 2's are all going to become 1s. So these 4 2's are going to become 8 1s. That means we're going to have a total of 10 1s. Now we have 10. Now we will have 10 irreducible representations matching our 10 classes. So that symmetry, that character table rule will be satisfied. And furthermore, 1 squared plus 1 squared, doing that 10 times, is going to be equal to 10, which is equal to order of the point group. So that means that rule is also satisfied well. So we'll do that in part 5 of this long derivation.